Hello friends! So just about a week ago I published a trailer video in which I presented this ducted propeller or ducted fan contraption powered by a washing machine motor. And in this video I'm now going through all of the steps of the building process, while I plan to make yet another video in the future where I will then test this thing and talk about possible uses for it. And since I'm not there yet, I'm still eager to hear your ideas about what this could be used for. So let us start at the beginning, and that is with this universal motor here that was salvaged from a German washing machine a couple of years ago. And I don't remember the exact make and model, but I guess this was a Bauknecht machine, but I might be wrong on this. But Miele, Siemens and other German manufacturers also typically use universal motors of this or a similar type in their washing machines, while in other countries induction motors might be more common. Well, however, this motor has a small pulley for a ribbed belt sitting on its front side on the motor shaft. And this little pulley was fitted onto the motor shaft back in the factory, and believe me, it is sitting extremely tightly on that shaft. And in order to get it loose, it is necessary to cut it open so that it loses some of its tension, and then it can be removed from the shaft. And as you can see here, I decided to use a cutoff wheel to cut off a section of the pulley alongside the motor shaft, while as far as possible trying not to harm the motor shaft itself. And at first glance you might guess that it would be easier to just cut a slit through the entire pulley from the side, but at least in this case that is not possible without also cutting into the ball bearing. And I'm not doing a perfect job here. I ground off a little bit of the motor shaft and also accidentally cut a little bit into the aluminum castings of the motor, but I was doing this without incapacitating the motor in any way, and I could then simply beat the shaft out of the pulley. And I have tried other methods with other motors that I had lying around. For example, I tried to heat up the pulley and then push the shaft out of the pulley, but that didn't work at all. Now maybe if you have a strong hydraulic press or something like that, you could maybe do it, but as far as I can tell at this point in time, if you only have an angle grinder, this is the easiest way to go. And here you can see that I accidentally ground off a little bit of the surface of the motor shaft while cutting off the pulley. I wish that didn't happen, but at least at this point I can say that in my experiments here so far, this was still within a reasonable tolerance and didn't do any harm. And here's the propeller that I bought for this experiment, and it says Menz S16/10. And what these names and numbers mean, well, let me just show you. Here I am on eBay, and what I did was really just looking for propellers. And what I found is this whole range of propellers here manufactured by a German company called Menz. And well, there are other manufacturers in other countries, but this is what I found. And you can see that these propellers are sold in different sizes and with different pitches. And there is a number pair like 16/10, and that means outer diameter of the propeller 16 inches. And the second number, that is the pitch, that means that in theory this propeller travels a distance of 10 inches per each revolution. And the largest propeller that you can buy here has a diameter of 27 inches, and that is around 68-69 centimeters. So you can see that it is possible to get rather large propellers really. And the first propeller that I bought that I'm using here in this video is a 1610 propeller, because it was reasonably large but still small enough to be fit onto the raft that I had built, and I took a medium pitch in order to just see what would happen. I have now also ordered a 16/14 propeller, and I will test that in the future. But before I can fit the propeller onto the motor shaft, there was another problem, and that is that the diameter of the shaft is around 11 millimeters, while the inner diameter of the propeller is only 8 millimeters. and that is why I used a whole range of drills to successively widen or bore out the diameter in 0.5 millimeter steps until I had reached 11 millimeters. And as you can see, now the propeller does indeed fit on the shaft. But what you can also see is that if the propeller is revolving very closely to the motor, that parts of it are hitting these protruding sections of this aluminium cast here. And I will have to cut some of the protruding material here before we can make this work. But before dealing with that, I decided to solve another problem first, and that would be to fasten the prop onto the shaft. And for that, another hole would have to be drilled through both of those parts, where then a split pin would be inserted. So after taking measurements, the motor shaft was punch marked and a 4mm hole was drilled very carefully through the motor shaft, and of course perfect alignment was key here. And after taking measurements again, the same thing was done to the propeller, of course. But before I could fit the propeller onto the shaft permanently, it was necessary to take care of those protruding parts in the front of the motor. For that, it was necessary to take the motor apart, and I'll show you that, even though this will probably not be necessary if you work on a washing machine motor yourself at home. Now, this motor unfortunately is not held together by bolts, but by cheap rivets, the heads of which I'm removing by drilling them open in the drill press. And here you can see a couple of bolts that I found in the workshop that I will use to replace the rivets once I put the motor back together. And I have now cut off those sections with the protruding aluminium cast parts, and now it was time to fit the propeller onto the shaft and use this so-called split pin, or in America cotter pin, here in Germany Splint, into the shaft and use that to fasten the propeller. Now there are several ways you could fasten a propeller on some kind of axle or shaft, but this was the first idea that came to me that seemed feasible and kind of easy to do, and until now it worked out well. Now, if you have any other ideas how you could fasten the prop on the shaft, then let me know about that in the comment section. Something else here, yes, I am weakening the propeller by boring out the drill hole in the middle of the propeller, as well as introducing that second 4mm hole for the split pin. But that is actually the main reason why I built this entire duct and taken some other protective measures, because it might be possible that the propeller will break during an experiment. And if you play around with this at home yourself, then please also take some precautions. Now, as I later learned, the larger diameter propellers, as far as I know, already come with an 11mm hole instead of an 8mm hole, so they might fit onto the shaft without any boring out at all. But now that the prop was fastened on the shaft for the first time, I felt the need to test it at least a little bit. And what I did was first to use a 12-volt lead acid battery to power the universal motor, and let's take a brief look at that. And of course that is only around 1/19 or 20th of the rated voltage of the universal motor, and that is why I've now connected it to my variable output voltage isolation transformer, and I'm cranking up the supply voltage to around 80 volts AC in this test. And these 80 volts are only about 1/3 of the rated maximum supply voltage of this universal motor, but this was the highest that I was willing to go without any protective measures, and that is why I wanted to build that duct first before going on with any experimentation. Now, what I did was to go to the local home improvement store, and I just bought like wooden leftovers really for under €5, and what I got myself are cross-laminated spruce, I guess, and MDF. And I first cut out a base plate for this duct from the cross-laminated wood, and then I used my jigsaw to cut out like half circles from the cross-laminated material and from the MDF, and I did that by improvising this tool here from a piece of wood, a nail, and a pencil that is fixated with a wood screw. And after having cut out all these parts, I just screwed them together with ordinary wood screws, and then I added 2 sideboards to strengthen this entire structure. And by the way, for every single screw that I used in this project, a smaller diameter hole had to be pre-drilled first, because otherwise it is very likely that the MDF will split open. And after that I took some aluminium sheets that had been lying around here for a couple of months, and I simply bent them into the rough shape of the half circle just with my bare hands, and that was very easy. But of course it was necessary to get it exactly right, and for that I used the cutouts of the half circles and kind of pressed the sheets down with a screw clamp. But because of the elasticity of the material, it wasn't possible to get the sheet in just the right form. So what I did next is to start at one side, drill a hole through the sheet, pre-drill the MDF, and use a wood screw to fasten it, then alternate to the back side and so forth, and work myself from the left hand side of the duct all the way to the right hand side. And after I had done that, I cut off that part of the aluminium sheet that we wouldn't need. Now, you could have calculated, of course, how large the sheet must be, but when you're doing these things by hand, you're always kind of off, so I figured it would be better to have a sheet that is way too long and then just cut off a section once I'm done. And now you can also see what these holes are good for that I cut into the sideboards, and that is for me to check if the sheet is really in the form that it's supposed to be in. With the lower section of the duct completed, it was time to think about how to attach the motor to the duct itself. For that I used this standard steel angle plate here and cut that to length and ground it into this shape. I then measured, punch marked and drilled a couple of holes through it so that this particular motor could be bolted to it. Then a second piece of steel, also made from stock, was bent and hammered into shape, allowing the motor to sit right in the middle of the duct. The 2 parts were bolted together, and this makes it possible in the future to potentially attach a completely different motor to this duct without a lot of hassle. Please also notice that all bolts and nuts used in this project are tightened with Loctite in order to prevent the bolts from shaking themselves loose. But before going on, the wires of the motor are attached to the steel parts with zip ties. In order to realize the upper section of the duct, 2 pieces of flat bar steel have already been measured, punch marked and drilled in many places. They are now being heated up at both ends in order to allow to bend the steel in a 90-degree angle without breaking it. After having cooled down the steel again, it is now bent into the rough shape of a half circle in the post vise. Excess material is then cut off with the angle grinder, and the 2 arches are screwed to the lower section of the duct. Now a very thin piece of steel sheet is used in order to determine the exact length that the aluminium sheet will have to be in. It is then cut to length, the edges are ground off, and it is bent into the rough shape of a half circle by hand. And on both sides, little slots are cut and bent into the aluminium sheet so that the steel attachment of the motor can pass through it. Temporarily, then the arches are loosened again to fit the aluminium sheet inside, only to tighten the bolts again. Here you can see that the prop can freely spin even though the sheet is not even attached to the arches yet. And this time that I'm quite sure of the exact length of the aluminium sheet, I will start to attach the sheets to the arches in the middle. I again drill holes through the sheet and then fasten the sheet successively, turning to the left and to the right. This time I'm doing that with M4 metric bolts and Loctite. And also temporarily, two small wooden blocks are attached to the lower section of the duct in order to hold the aluminium sheets in place also in the middle of the duct. Then some duct tape is used in order to close the little gaps between the two sheets. So since I performed these initial tests here about a week ago, I have now added some wire mesh to both openings of the duct, and I'm also wearing goggles whenever I turn this on. Furthermore, I wanted to say that if you power this from batteries, you have seen that it works with a 12-volt battery, but it is spinning very slowly. If you want to power something like this from batteries but have it spin faster, then you can, for example, use car inverters like these two here, or the inverter from an uninterruptible power supply. Now, another thing that I wanted to mention is that a lot of the work that went into this project was to actually physically building the duct itself, and some of you might have wondered why I've put so much time into that. Well, I wanted to find a way of building a duct like this for any size, so if I were to buy larger propellers, I could simply apply the same technique. It is kind of flexible, but also grueling work. So another way, a very much easier way, would probably be to find some kind of pipe that just has about the right diameter, or maybe a plastic barrel or a steel barrel or something like that. So I have shown you the list of the available diameters earlier in the video, and if you know something that could be used as a duct, for example a barrel or something like that, that can be bought cheaply and does not have to be manufactured first, then please comment about that in the comment section. And also, people have been asking about a speed controller for these universal motors, and I have been talking about that in some earlier episodes of mine. And the answer in this particular application is that when the pitch and the size of the propeller is in a certain range, there is a constant load on the motor, which prohibits the motor from spinning too fast without really the need for electronic control. But I will have to do more testing with this motor in different propellers and measure how fast it is spinning and so on to give a conclusive answer to that. As far as speed controllers for universal motors go in general, yes, I am working on it again, but I cannot yet promise when that will be finished, when there will be sufficient results in order to present them in an extra video. As far as this propeller contraption goes, I want to make another video, at least one, where I will test it and maybe think of some interesting applications or experiments, but that'll probably have to wait a couple of weeks since I have now returned to Cologne, and the next video will be about something different first. But you'll hear more about this in the near future. So I hope you liked this, and see you soon.